Hello, my name is Daniel. We'll start the presentation by going over the dataset, doing some exploratory data analysis, feature engineering, and then we'll talk about various classification models used. Breast cancer is the most diagnosed cancer and the leading cause of death in Canadian women. This project applies machine learning for an early detection. We're using the Wisconsin Breast Cancer Diagnostic Dataset, created in 1995 at the University of Wisconsin-Madison. It includes 569 samples, each with 30 extracted features that describe the cell nuclei. These features define tumor size, shape, texture, helping differentiate benign from malignant cases. Key ones include radius, perimeter, area, compactness, and concavity. On this slide, you can find additional information about the features. The dataset also records each feature's mean, standard error, and worst values, providing a more comprehensive view of the tumor's characteristics. Our dataset contains 30 measurement features, a diagnosis target variable, and an ID. Of the 569 cases, 357 are benign and 212 are malignant. Benign tumors are localized and non-life-threatening, while malignant can spread rapidly. We encode them as 1 and 0 respectively. Here is a proportion of tumor types showing more benign than malignant cases. The objective of the dataset is to help us build models to improve diagnosis speed, assist doctors with predictions, and reduce unnecessary follow-ups. This is our initial workflow we followed to pre-process our dataset. The correlation matrix shows multicollinearity between some features, and looking at the top highly correlated features, we see that radius, area, perimeter have a strong relationship. We then use violin plots to visualize the distribution of key features like mean radius across benign and malignant tumors. This allowed us to compare not only the central tendencies, but also the spread and shape of the distribution between the two classes. Here is the violin plot for the standard error features by tumor class, and finally, the violin plot for worst features by tumor class. We found that larger values of radius, perimeter, area, compactness, concavity, and concave points are linked to malignant tumors, while texture, smoothness, symmetry, and fractal dimensions don't strongly indicate a diagnosis.
Hi, my name is Saba, and I'm going to take you through the first model we chose, which is logistic regression. It's a simple but effective classifier that helps set a baseline. We used a 70-30 train test split with stratified sampling to maintain class balance. Logistic regression provides interpretable coefficients, making it a great starting point. Our dataset contains 569 patient observations, each represented by 30 features derived from digitized images of fine needle aspirates of breast tissue samples. Each case is labeled as benign or malignant. We modeled the distribution of the features for each class using Bayes' rule to estimate the probability of a tumor being benign. If the log ratio of probabilities is greater than 0, we classify it as benign. The logistic regression model uses a sigmoid function, also known as logistic function, to map the linear combination of predictor variables to a probability between 0 and 1. To train the model, we use maximum likelihood estimation, or MLE. The likelihood function represents how well the model fits the data. Since direct optimization is difficult, we use log likelihood and optimize it via gradient descent. To refine our model, we used AIC to help select the best features. AIC forward selection is a useful method for model building. It systematically adds variables to the model one at a time. Each variable is chosen based on how much it improves the model's fit, as measured by AIC. The process continues until no further improvement is possible. We evaluated performance using accuracy, precision, recall, and F1 score. The model achieved 96% accuracy with high precision and recall, indicating strong predictive capability. The ROC curve assesses the model's performance by comparing the true positive rate to the false positive rate. Our model achieved an AUC of 0.99, demonstrating excellent ability to distinguish between classes benign and malignant.
Hi, I'm Ling, and I worked on the Gaussian naive Bayes model. Our second model is using the Gaussian naive Bayes approach, where we use the Bayes rule and assume conditional independence. We base our model on a single distribution, in this case Gaussian, for training and predicting. To select the most likely class, we simply argument max the posterior under a probabilistic decision rule. In practice, we calculate this posterior using the log likelihood instead, because sometimes the likelihood of the probability of class given data approaches 0 and fails to compute a useful result due to how floating point numbers work. By using log likelihood, we can stick to using addition of negative numbers instead and not lose any information. Here's a review on the Bayes rule, where you can see how the posterior, prior, and likelihood all relate. To learn the prior and the Gaussian parameters, we simply use the MLE calculated from the sample. We go feature by feature and create many different feature-specific distributions to compare under different classifiers. Using Gaussian naive Bayes resulted in an F1 score of 0.96, and also along the way produced some distributions of features we can look at. We can see that some features are terrible classifiers, such as smoothness error on the left, and gradually becoming great classifiers like worst concave point on the right. This is a good way to visualize which feature are the most important when classifying and giving us some insight, like how we could focus on using concavity as an early indicator of a malign tumor. Here's a confusion matrix. Notice how we have very little type 2 error, which is very important for medical fields, where you would like to avoid false negatives much more than false positives. In summary, Gaussian naive Bayes offers a simple model that trains quickly and works well enough, on top of also giving potentially valuable insights on the data.
Hi, my name is Daniel Malakovsky, and I'm a third-year student specializing in the math statistics stream. Another approach involved using TensorFlow to develop a deep learning neural network. TensorFlow is a powerful framework for building and training machine learning models, and this is why. First of all, it is capable of handling large-scale machine learning with extensive datasets, making it well-suited for deep learning. TensorFlow allows us to easily design and train the neural network, allowing our model to learn complex patterns in cancerous data. Also, the results can be easily interpreted using existing techniques such as SHAP. Now let's see how well our model distinguishes between benign and malignant tumors. We receive a test accuracy of about 0.97, meaning our model correctly classifies 97% of the cases in the test dataset, which is an indication of strong performance. As you can see, since our values for precision, recall, and overall accuracy are within the range of 95 to 99%, the TensorFlow model performs exceptionally well. Looking at the model's learning process by seeing how the training and test accuracy changes over epochs, we notice that both curves increase together, showing the model is steadily improving its predictions. Since there is no large gap between the curves, this means the model is not overfitting. We have a high overall accuracy indicating there is no underfitting, and the model has learned meaningful patterns from the data, giving us confidence our model is ready for real-world predictions. Using SHAP, let's see which features have the most influence on our model's decision-making when classifying benign versus malignant tumors. We see that the top 3 most important features are mean concave points, mean concavity, and worst radius. Tumors with more concave points, higher concavity, and larger in size have a higher chance of being malignant. What are the key takeaways? From our findings, we see that tumor shape is more predictive than just size alone. Since worst radius captures extreme values, It provides more insight for malignancy than just the average size. As seen earlier, because worst radius and mean radius are highly correlated, SHAP prioritizes the more impactful feature while downplaying the other.
Hi, I'm Varun. I'm a fourth year statistics specialist in the machine learning and the data mining stream. So let's start with Gaussian process classification. A Gaussian process is a stochastic process where any finite set of values is jointly Gaussian. It is defined by a mean function and a covariance kernel that captures similarity between inputs. And we use this Gaussian process to represent the prior over latent functions which are not directly observed. So it is a Bayesian non-parametric model for classification that learns a distribution over these latent functions, these latent classification functions. Instead of a fixed decision boundary, it provides us a probabilistic decision boundary, and that is used to classify points into benign or malignant based on the input. Effectively visualize and have more efficient results, we will utilize PCA to go down from 30 dimensions into 2-dimension features, which are the first two principal components that preserve most of the variance and enable us to effectively run this algorithm since this is order n cubed. So high dimensional outputs will make it computationally expensive. So let's look at the learning process. So we choose the RBF kernel that which encodes our assumption that similar points should have similar outputs. Then we place a Gaussian process prior over these latent functions, meaning we're working with distributions over functions, not a single function. We use Laplace approximation to compute and approximate posterior, since exact inference isn't traceable in classification. The model then maximizes the log marginal likelihood using MLE to tune kernel hyperparameters like length scale. Finally, we can classify new points by computing their predictive probabilities from this posterior. So this is what the hyperparameter tuning and our entire learning pipeline looks like. Then we also have a learning curve where we use five-fold cross-validation. Both curves are relatively stable with a small generalization gap, suggesting that the model is not overfitting. And another key feature here is GPC achieves consistently high performance even with small training sets, which is a very known strength of Bayesian models. So here we can see the decision boundary on the PCA reduced data. So here the black contour is the 0.5 probability threshold. These are smooth nonlinear boundaries, and these are interpretable under uncertainty around the boundary. Another perspective of this is the uncertainty map, where the uncertainty is is the highest at the 0.5 probability mark. This is important in medical cases because doctors can flag these patients as borderline or ambiguous cases and flag them for additional screening. Using the PCA reduced feature, GPC achieves 94% accuracy on the test set. The confusion matrix shows balanced performance across both classes, and the F1 score indicates a good trade-off between precision and recall. So here are some benefits, drawbacks, and the clinical relevance of this entire model in early cancer detection. It provides uncertainty where predictions helpful in a high stake domain like this. But the drawback is that it is computationally expensive and not ideal for very large data sets, which are again important for medical cases. But it enables risk-aware decision support. So this helps doctors not only know what the model predicts, but how confident it is. So in conclusion, all of our models give us different perspectives into our data, but logistic regression can give us interpretable coefficients, confidence intervals, p-values, and other information. Then naive Bayes can model the distribution directly, and GPC can offer a calibrated uncertainty and flexible decision boundaries, which are probabilistic in nature. And neural networks can give us a very strong performance and a feature importance analysis, which can tell us what features contribute how to our predictions. And with that, we conclude our presentation. Thank you.